Given this rational expression, we're going to divide using polynomial long division to find the quotient and remainder. Let's first notice that this rational expression is considered to be improper because the degree of the top polynomial is greater than the degree of the bottom polynomial. The degree of the top is 3 and the degree of the bottom is 2. So in order to divide these two polynomials, we'll start with our division box, and the dividend is going to go inside the box. The dividend polynomial is 2x cubed minus 8x squared plus 7x minus 13. The divisor is then put outside here, and now we're ready to begin. We start by looking at the first term of the divisor and comparing that to the first term of the dividend. We ask ourselves, 2x squared times what is 2x to the third power? Well, 2x squared times x is 2x to the third power, so x is the first term of our quotient. Now it's time to multiply. We need to multiply this first term of the quotient by every bit of this divisor, which means that we need to distribute the x into the divisor. So x times 2x squared is 2x cubed, and this first term should always match the one above it. And then we have x times 5, which is 5x, and we want to line that up underneath the other x term. Now it's time to subtract this polynomial from the original dividend. And we do that by distributing a negative into the second polynomial, which will cause us to get a sign switch. So the rhyme that we use that helps us to remember to do that is to draw the line and change the sign of each of these terms. We also circle the new sign just to help us keep track. This first term is going to drop out, and then we combine like terms. If there's no other x squared term, then we just bring down the negative 8x squared. Essentially, that's negative 8x squared plus 0. And then for the x terms, we have 7x minus 5x, which is plus 2x. And negative 13 is the only constant, so we just bring that down. In other words, we could think about that as negative 13 plus 0. So now we hit the repeat button and we start again, treating this polynomial as our new dividend. We compare the first term of the divisor to the first term of the new dividend, and we ask ourselves, 2x squared times what is negative 8x squared? 2x squared times negative 4 is negative 8x squared. So negative 4 is the next term of our quotient. And now we multiply. The negative 4 is to be multiplied by every term of the divisor. So negative 4 times 2x squared is negative 8x squared, and again this first term should match the one above it. Now negative 4 times positive 5 is negative 20, and we want to line that constant up underneath the other constant term. And now again it's time to subtract, and the rhyme that we have that helps us to remember to do that is that we draw the line and change the sign of each of these terms, circling the new sign. This first term should always cancel out, and then we combine like terms. 2x combined with nothing, or 2x plus 0, is just 2x. And then the constant, negative 13 plus 20, is plus 7. Notice that the degree of this remainder down here is 1, because the highest power on the x term is 1. And the degree of the divisor was 2, because the highest power on the x term in the divisor is 2. So since the degree of the remainder is less than the degree of the divisor, it's time to stop and clearly identify the quotient and the remainder. The quotient is this expression up here, so x minus 4, and the remainder is this expression down here, so 2x plus 7. So this is the answer to part A. So now for part B, we're asked to rewrite the rational expression using the form quotient plus remainder over divisor, which again is how we would come up with the mixed number version of an improper fraction. And so this also works for improper rational expressions. We can rewrite it as the quotient, which we found to be x minus 4, plus the remainder, which was 2x plus 7, divided by the divisor, which is 2x squared plus 5. Remember, this quantity down here is the divisor. So now what we have is essentially the mixed number version of the original improper rational expression.